Okay, so this is the plan for today. I would like to finish until 3.4 today. Let's see how far we get. I would be happy also with 3.3. So we are going to talk about thermodynamic state of a system. We're going to talk about the difference between heat capacity and specific heat. You have heard these terms in chemistry. So for those of you that have heard these terms, raise your hands. Those of you who actually remember what they are, raise your hands. Okay, excellent. So a couple of you remember that. That's good. We are going to re-revise them. For those of you that have not had them yet, this is going to be our first introduction. It's not as hard as what you think they are, as long as you understand where they came from. So we are going to start there. Let's start at the beginning and talk about the thermodynamic state of a system. What is a thermodynamic state? The thermodynamic state of any system. What is a system in thermodynamics? Anything that we are studying at this moment. Okay, that is a system. What defines a system? Boundaries. What is around a system? Surrounding. So these are words we are going to get familiar with. So a thermodynamic state of a system is determined by specifying a set of measurable properties of the system that are sufficient to determine all other properties of the system. So since we are in thermodynamics, what do you think those measurable quantities could be?
Temperature.
Temperature. But what is the measurable quantity? Temperature of the room. How do we measure the temperature of this room if this is our system? Somebody said thermometer. Put a thermometer here. Read what it says. Done. What else can you tell me about the system? Volume of the system. Is it a big room? Is it a tiny room? Pressure. So some of those measurable quantities include temperature, T, volume, V, pressure, P. Now, if we consider ourselves to be a system, are we a uniform system? No, right? Are we uniformly distributed in this room? Are stuff uniformly distributed in this room? So we are a complex system. That is an engineer's problem, to study complex systems. We will study simple systems. So systems that we will study will be mostly simple systems. And when we do have a complex system, what do you think we're going to do?
Simplify it again.
How do we simplify it?
break it up into parts?
Yes. So if you have a complex system, break that system up into parts until they become a simple system. And then you study those subsystems and then put them all together. Does that make sense? So anytime we have a complexity, we will break that complexity for complex system, divide either experimentally or theoretically, conceptually, into simple systems. Okay. Other things I have to tell you. Okay, we've talked about this before, but I just want to review it. So when a system changes, in thermodynamics, we call it undergoing a process. And the different states that the system evolves through is called the path of process. Okay, I'm going to write that down. Number one. Number two, the number of states that the system evolves through is called the path of a process. Also called transformation. So you'll hear these two words interchangeably. Okay. Another thing, number three, cyclic process. If a system goes through state A to B to C to D back to A, that is a cyclic process. It has to return back to state A.